Good morning, everyone. So, today we are going to see a combinatorial problem related to graph theory, which we are going to solve using the concept of recurrence relation and generating function. So, to begin with, let us understand the concept of a tree. So, tree is a connected graph having no cycles as a subgraph. So, connected graph means that, for example, if I consider this graph, then this graph is not connected. This is also not connected because I can label them also, because you can see that there is vertex 1 2 3, and from 1 to 3 I cannot reach to 7. But if I introduce these edges, then the graph becomes connected, and now this connected graph has a cycle. That's why it is not a tree. So this is a tree because it has no cycle, but now this graph has a cycle, so that's why this is not a tree. So rotate tree. So let T be any tree and you fix a vertex R of tree T. Then a rooted tree is the ordered pair T comma R, where R is said to be root. So let's consider this example. If you see these two are trees, the other observation is that both are isomorphic. They are same, because what I can do is that I can take this vertex fix and I can take these two on this side and I will get the same graph. But when I fix a root, then in this graph, this root has three vertices adjacent to it, but this root has only two vertices adjacent to it, and there can be any other differences also. It means that as a tree they are isomorphic, but as the rooted tree they are different. So once we have rooted tree, we can talk of some relations. For example, if I start with A or start with U, then the parent of U is A. Yes, children's are B, C, and D. So parent of U are A, children's are B, C, D. Ancestors, which means parents, grandparents, and so on, are A and R. And descendants, so children, grandchildren, and so on, B, C, D, E, F, G, H. All are grandchildren. So this is how we can talk of the different relationships in a rooted tree. And if you consider E and F, since they are at the same level, they are the siblings, or their parent is same. So that's why they are the siblings. Now once you introduce the order in a rooted tree, it becomes a ordered rooted tree. So a rooted tree in which left right order of every set of siblings is specified. So again, if you see these two trees, as a rooted tree they are isomorphic, but as an ordered rooted tree they are not, because here the order of the siblings are A, B, and C, but here it has been changed A, C, B. So now binary trees are the ordered rooted tree in which every vertex has at most two children. Yes, if you see the previous example, then you can see that there can be, I can easily introduce this one or so on, many more childrens. But if you restrict the number of the children, something like this, then we call it a binary tree. So binary tree is a ordered rooted tree where every vertex has at most two children. So you can quickly try to draw all binary trees on four vertices when the root has non-empty left child and right child. So this is the root, left and right child are fixed. So now there are four possibilities. Either you can go this one or this one, this one or this one. So total four possibilities are there. Now there comes a combinatorial problem which says that how many rooted binary trees are there with n vertices. Yes, so we are going to solve it or address it using the concept of generating functions. So let us denote the number of the rooted binary trees with n vertices as Cn, which we call as Catalan numbers. So it's easy to see that we just assume that C naught to be equal to 1. C1 there is only one vertex, so it's 1. For C2 either there is a left or right possibility, that's why it's 2. Now quickly try to compute C3. You will realize that the answer comes out to be 5. Yes. Now there comes an important observation which says that any rooted tree can be viewed as two binary trees. So if you see this rooted tree, then it can be seen as the sum of two binary trees, and you introduce a root and make them the children of this root. So as two binary trees joined into a new tree by introducing a new root vertex and making the children of this root the roots of the original trees. Yes. So if we follow this rule, then we can see that we can write C3 as follows. So C naught means there is nothing. So that's why this is C naught and then this is C2. Now for C2 it's 2. So 1 dot 2. Then C1 C1. So C1 is simply dot and introduce a root and make it adjacent. And value of C1 is 1. So 1 dot 1. Again C naught is 1 and C2 is 2. If you add them, the answer comes out to be 5. You can try it for any number. So it's an enumerative approach. So similarly from C3 you can move to C4, C5 and so on. But it means that you can write Cn as follows: summation I from 0 to n minus 1 Ci Cn minus I minus 1. Yes, now this is a recurrence relation and I want to solve it. So we haven't seen such recurrence relations. We have only seen the homogeneous, non-homogeneous with constant coefficients. So to solve it, we will introduce the concept of generating function. So let us say that I call f as summation Ci x raised to the power I. Yes. Now if I say f square, then f square will be summation Ci x raised to the power I and summation Cj x raised to the power j. Now if I want to compute the coefficient of x raised to the power n in f square, then the idea is simple. If I pick x raised to the power n minus I from here, that gives you Cn minus I, and multiply it with x raised to the power I and Ci, and then take the summation from 0 to n. I is moving from 0 to n. So this gives me the coefficient of x raised to the power n in f square. Yes, so I will get all these terms. So this is the summation. Now if I compare it with this summation, so here what I am getting, I from 0 to n and then Ci Cn minus I. If you compare these two, then you can say that you can write f square as summation Cn plus 1 and x raised to the power n, because this is equal to Cn plus 1 from this formula. Yes, now I want to see a relation between f square and f. So this is my f square. Now in f square, the first term is C1 x raised to the power 0, C2 and so on. So if I introduce C0 and multiply it by x, so first I multiply it by x, so x f square, that gives me Cn plus 1 x raised to the power n plus 1. So now the summation starts with Cn x plus C2x square and so on. The only term, the first term is missing C0. So I can add and subtract C0. So C0 would be merged here and minus C0 would be minus 1. That gives me f. So it means that x f square plus 1 is equal to f. Just read it and it would be clear. This is my f square. Now I multiply it by x and add 1 so that it becomes f. And that gives me a quadratic equation as follows, from where I can get the values of f. Now here the observation is there are plus minus signs are there. Yes, if I see the plus sign and if I take, what I know is that my f of x is summation, this is how I assume it is, cn x raised to the power n. It means f of 0 is c naught, which is equal to 1. So if I take limit x tends to 0 and 1 plus root 1 minus 4x by 2x, the numerator is 1, denominator is 0, it goes to infinite. But if I take 1 minus, then it becomes 0 by 0 form. So it means I need to differentiate it. If I differentiate it, then you will see that it turns out to be a finite term if I apply the L'Hopital rule, or even it turns out to be 1. So it means that 1 plus root 1 minus 4x by 2x does not work, and the solution to this one is 1 minus 1 minus and root 1 minus 4x by 2x. So this is my required f of z. Yes. Now I just need to simplify it using binomial expansion. I can write 1 minus 4z raised to the power half as follows. I make some rearrangement and substitute it back into the formula f of z. That gives me this relation. If I further simplify it, then I realize that the coefficient of z raised to the power I, because that is Ci, or Cn is the coefficient of x raised to the power n, it turns out to be in the closed form as follows, which is the Catalan number. So Ci is, or Cn is 1 by n plus 1 and 2n n. Okay, so it's a very well-known result because many combinatorial problem and their solutions comes out to be Catalan number. For example, if the problem is that we want to count the number of the ways to triangulate a regular polygon with n plus 2 sides, then it comes out to be, the number of the ways comes out to be Catalan number as follows. So for n plus 2 means 3 sides, it's 1. For n plus 4 2 sides, it's 2, and so on. Now given a triangular region composed of n blocks on a side, in how many different ways can the region be tiled with exactly 4 rectangles? Something like this. So there is a triangular region and I want to tile it with 4 rectangles on one side. And 4 rectangles are there. So if you compute C4, which is 14, then you will realize that the number of ways are 14. So that's all from today's class. Thank you.